It is my great pleasure to introduce Dr. Sampen, who has made significant contributions to the field of osteoarthritis and associated pain over the past 20 years. And with extensive experience in academic medicine, Dr. Sampen has taught and published extensively with over 190 full-length peer-reviewed papers and book chapters and over 250 research abstracts. And she has received, if you want to go to a lab that's got tons of money, Dr. Sampen, who has received over $10 million, 10 million as in US dollars, which is like $1 billion Canadian dollars in research funding, and has served as editor-in-chief on the editorial board of numerous international journals. Dr. Sampen's research has focused on identifying key pain determinants in OA, with a particular emphasis on the roles of nerve-promoting factors. So she's worked on NGF, TRK, and VEGF signaling and she has done this through a multidisciplinary collaborative research. So just to let you know, this is one of the main way to go. So whatever you do is go multidisciplinary. So she's done this with Dr. Olsen at Harvard Medical School, and she has found these pathways that can transform asymptomatic joints to painful ones with the upregulation of these factors, which are NGF, TRK, and VEGF signaling, which closely correlate with the high density of synovial sensory fibers in the knee joint. So her team has also shown promising results in using mesenchymal stem cells for cartilage tissue regeneration in an OA rabbit model. So this supports phase 1 clinical trials. As a dedicated teacher, as you can see, she's very well-rounded. She doesn't just do research, she also teaches. She has directed 4 key teaching courses and mentored over 80 trainees in her lab, including fellows, residents, postdoc fellows, graduate and college students, and medical students. So her successful mentees have gone on to receive promotions and funding from prestigious organizations such as the Arthritis National Research Foundation, and also the premier for grant, which is the NIH. And she also contributes not only to our research, not only to training, but also to service. And this extends beyond academia, as she has worked in various capacities for local and national VA centers, and she participates in several oversight committees related to research development, research safety, career advancement, policy, advocacy, and social work. She is currently a certified VA national approved PMDB instructor. So she's advocating for a non-violent environment for veterans at the VA. So please join me in welcoming Dr. Sampen to today's talk.
Thank you very much for your generous the introduction. I was there at McGill University 10 years ago, 2012, and then at the time I gave a seminar about the low back pain study. And I met my old friend, Faxon, at the time, and I'm so glad to see you again here. So I'm very excited. So nothing to disclose. And my talk is about OA. The human body has just so many joints, like you can see here. Unfortunately, every joint can have osteoarthritis. So our primary interest is in knee joint, here you can see, and spine disc degeneration. That can cause low back pain. So today my talk is only knee OA pain here. So pain is the primary reason why we need medical help. And knee OA affects more than 32 million Americans Let's talk about the globally. It's about more than 250 million people. It's kind of a scary number. So now this expected to be about 78 million, and I'm talking about in US by 2040. It's only less than 20 years left now. So it's very worries about me. So there are no effective OA treatment drug yet. And about, the second student talking about the opioid crisis, but more than 50% of OA patients are treated actually with the opioid because they don't know what to do about the pain, OA pain. So many of them became addicted, unfortunately. Even worse, clinical data show that the OA patient easily develop depression that aggravates joint pain. So I won't present data today about the depression study, but we are currently working on OA pain and depression comorbidity in our experimental comorbidity OA model. So I hope I can have a chance to share the data with you again in the future. So let me have a laser pen. Okay, so why did we get OA? So here are OA risk factors, including injury, aging, obesity, alcohol, and disruption of circadian rhythm. Also, genetic background is a big portion of risk factor. Now, there are surgical and non-surgical treatment options here. The first non-surgical treatment option include painkillers over the counter. The second student talk about the NSAIDs or aspirin, ibuprofen, but those NSAIDs are not good enough, not strong enough to cure the pain. So that's why people go for the looking for more strong anti-pain, the drug like opioid that can cause a lot of a society problem here. Now, the non-surgical treatment also include intra-articular injection of steroid or hyaluronic acid, which is very popular at the moment in the hospital, or cell-based therapy. Now getting more popular, the stem cell, intra-articular injection stem cell, or exercise and acupuncture has been proven to be effective. The picture shows here how intra-articular injection is done, because this is what the people usually do. They cannot do anything about this pain. So this is a HA injection in hospital. Now, surgical treatment options include minimally invasive surgery. If nothing works, then joint replacement surgery. But you have to think twice before you do the surgical procedure, because there are so many complications involved in major surgical procedure. And more importantly, surgery will not guarantee pain-free life. So bottom line is there is no cure for OA yet. OA can be defined as age-related cardiac wear and tear, as I mentioned at the very first slide. However, OA is not only cardiac disease. This is a whole joint issues here. There are multiple joint tissues, including cartilage, synovium, subchondral bone area, and meniscus. You cannot see from this picture, but meniscus is both sides like this. These tissues will cross-talk through synovial fluid filled in the cavity in knee joint. Now, activated chondrocyte in OA cartilage overexpresses pro-inflammatory cytokines such as interleukin-1 or nitric oxide, which in turn stimulate cartilage-degrading enzymes, including matrix metalloproteinase 13, which is very potent collagenase, and aggrecanase such as ADAMTS4, ADAMTS5. Now, cartilage breakdown products stimulate the synovium. Okay, they all cross-talk, I mentioned that, which in turn stimulate more pro-inflammatory cytokines and pain mediators. In cartilage, there is no vascularization, there is no blood vessel, and no neurons. So question is, where the pain comes from. Okay, so peripheral joint tissue damage can be sensed by primary apparent nociceptor. We call it Z fiber or A delta fiber, causing sensory neuronal plasticity in dorsal root ganglia, peripheral neuronal system, regulating multiple pain modulator, which in turn enhance the excitability of the neurons and spinal dorsal bone and brain. So we feel pain in the brain through ascending pathway going through here. Now, pain transmission process from peripheral tissues to neurons to central nervous system magnifies and accelerates the pain sensation. So we call it pain central sensitization. So OA-induced chronic pain is a centralized pain. Let me go through a very little bit of type of chronic pain, just background here, and very brief. One is nociceptive pain. This is caused by tissue damage. If somebody punches you, pinches you, or if you burn your skin, all those give you pain feelings. So, and when damaged, the tissue heals, the pain just gone. Pain issues can be resolved. It is reversible. You can reverse those the process. Now, neuropathic pain caused by nerve damage. For example, is the diabetic neuropathy. Unfortunately, it is very hard to reversible. Once you damage your neuron, that's it. Really have a reversible about the neuropathic pain. Now, inflammatory pain is caused by inflammation. For example, rheumatoid arthritis or inflammatory bowel disease. Those highly inflammatory conditions, you can feel pain. Now, mixed pain is very easy to, and now mixed pain as it is. The name say that pain is caused by mixed various pain, including nociceptive pain, neuropathic pain, inflammatory, all together, mixed pain. In 10 years ago, we generated 3 different OA models. NIA model is here. NIA model is a chemical, a very toxic chemical you articularly inject in knee joint and cartilage degenerate is model. And SCLT-DMM is surgically induced animal OA model. We compared all those 3 different OA models with neuropathic pain model we generated by sciatic nerve ligation. So based on our study, we conclude that the component of nociceptive OA pain overlaps with neuropathic pain and inflammatory pain pathway. All those components is in the OA pain. So another word is OA pain is mixed pain. Targeting pain that is very specific to OA is very important. It is because there are many different pain pathways we just went through there. There is including nociceptive pain, inflammatory pain, neuropathic pain. So it is almost unrealistic to have just a single drug can take care of all these different pain pathways, just like a magic button. Okay, we can't have that. For example, there's a hugely different mechanism between diabetic neuropathy and OA pain. So pathophysiology of diabetic neuropathy is because of the damaged nerve. The nerve disappears. On the other hand, OA pain caused by too much nerve ingress. I will show you the picture of too much nerve ingress in knee joint that can determine OA pain. Therefore, we must identify OA specific pain to control OA associated pain. So our study goal is to identify and validate OA specific targets to develop OA disease modifying drugs. So I will talk about 2 OA specific targets to identify over the several years here. So a nerve growth factor and VEGF, vascular endothelial growth factor. Key members are shown here. Now first, nerve growth factor. If someone with a genetic mutation of either nerve growth factor and TREG-A, they don't feel pain. So someone may say, wow, they are lucky. But that is not the case because they don't live very well. As you know, in normal condition, pain is our first defense mechanism. Okay. These are human knee joint. We are very grateful for these tissue donors and the family members because without them, we won't be able to advance our research in medical research. So from healthy, shiny, and snow white, perfect cartilage zero normal cartilage here, early OA is group 1 and 2, advanced or late OA stages, groups 3 and 4 here. One may think that person with grade 4 here experience the worst pain. However, all of them are actually asymptomatic donors. Nobody feel pain. There's no medical history of they suffered from any kind of joint pain because of the osteoarthritis or cartilage degeneration. This is one of the mysteries we call it orthopedic field mysteries. Okay, so there's no close correlations between the degree of cartilage degeneration and I'm talking about pathological degrees and the degree of pain. There's no correlation. So surprisingly, up to 40% of patients, OA patients, are symptom-free, which is nice. But how can you make those 60% symptomatic patients to 40% asymptomatic pain? So the mechanisms by which OA develops from an asymptomatic, that means pain-free, to symptomatic condition, that means painful condition, is our critical gap in our knowledge. So what we're trying to show is our finding demonstrate that synovial augmentation, synovial increase of nerve receptor is cognate receptor TREG-A, both directly correlated with the OA pain sensation in human. Okay, here's the result. So I mentioned that those guys are all donors, are no pain in history. So we took out each sample synoviums, and then we targeted nerve receptor or TREG-A. This result shows nerve receptor. We didn't see much differences in nerve receptor. Grade 0, grade 4, I don't see any differences. There's no trend of increase whatsoever. However, when we compare with OR samples, operating room, those patients going through the surgical procedure because of the extreme pain, those guys, the samples show highly increased nerve receptor here. We found very similar data from TREG-A, but I didn't include it here. Okay. Major function of nerve receptor is nerve growth. They grow nerve. That's the name of nerve receptor. So again, from 0 to 4, this time we took out those synovium cells and targeted this time PGP9.5, which is a neuron markers. So we want to see how much neurons or nerve fibers within the synovium. So we didn't see much differences. All same. I don't see any up and down here, or there is no pattern of expression. Now again, we compare the OR sample. We can see that there is a highly stimulated nerve ingrowth in the synovium. So the sensory neuronal distribution in the synovium directly correlate with the joint pain sensation. All right. So in painful knee OA, synovial nerve receptor is overexpressed. Now we saw that. And then next question is how this overexpressed nerve receptor is associated with the joint pain. What they do once it produced, so what? So that's why we hypothesize that in painful OA, this such overexpressed nerve receptor could be transported to the DIG soma cell through TREG-A receptors that present on the apparent sensory nerve terminals, okay, which may promote axonal outgrowth into the joint, causing more pain. So make it much easier, we visualize this process here. In OA, synovial cell produce a lot of nerve receptor here, and that click with TREG-A, with the cognate receptor TREG-A on the nerve terminal here, and retrogradally transport to the DIG soma cells where stimulating further neuronal outgrowth factors and pain mediators. Okay? So transportation of the nerve growth factor, the knee, from here to DRG, it takes 3 days based on our time course experiment. So what we did here is the experimental plan to see that. So to test increase the transportation of the knee from nerve growth factor from peripheral knee joint to the DRG in OA condition, we compared with the healthy knee together. So first, we induced the knee OA here to compare with the healthy one, and intra-articularly injected labeled nerve growth factor. We have to differentiate with the exist. Your body already have a nerve growth factor, so we have to separate from by labeling nerve growth factor by biotin. So labeled biotin conjugated nerve growth factor. And we waited 3 days because it takes 3 days up to go to the DRG. So we harvested innovating DRG L3, 4, 5, and we detected biotin labeled DRG in the DRG, and it labeled the nerve growth factor in the DRG sensory neurons using streptavidin that targets biotin. All right, so this is a result. So in sham animal, which means no joint pathology whatsoever, not much we can see the biotin transportation. That means nerve growth factor here. Now, in advanced OA injection, this is what we found. We have a lot of the biotin conjugated, the nerve growth factor move from knee joint to DRG. So we say suggesting abundant sensory nerves in the OA facilitated nerve growth factor transportation from knee joint to DRG. So we try to understand that what is the nerve growth factor TrkA can do in OA pain. So we induced OA in mice with global conditional deletion of TrkA. Okay, so this is red color, and compared with the pre-negative, which is wild type here. So global deletion of TrkA in mice simply showed no pain. I'm sorry, I don't know my audience background, but this is a mechanical allodynia pain test. Is up here because this is threshold, is up here, is no pain line here. And very pain sensitive, the pain level is lower here. It's okay. And I am sorry, I did not really explain very clearly by including all the pictures or whatever. In this case, probably it takes too long, my seminar, so I just removed all those things. So anyway, this red color is no pain because so close to no pain level here compared to this white type. White type is in pain, the black line here. Nevertheless, despite of this pain, no pain level, still it did not protect cartilage from degeneration. You can see the exactly same white type, all degenerated, this mice. Okay, immunofluorescence staining here, D, bigger D, targeting nerve growth factor or TrkA in DRG sensory neurons to show the reduced expression of TrkA or nerve growth factor in the DRG sensory neurons. This reduction is correlated with the reduced pain sensation, which is shown the bigger A here. Now we generated tissue-specific deletion of TrkA in mice. Number one is a sensory neuronal specific deletion of TrkA, which is a red color. Also showed no pain and still did not protect any cartilage from degeneration. Just like the global deletion of TrkA in mice is showing exactly same cartilage degeneration, wild type here. Okay, so immunofluorescence staining confirmed over 90% of TrkA reduction because this is a conditional knockout mice, and also reduced the expression of nerve growth factor in the DRG sensory neuron. So this is a DRG, okay, DRG immunofluorescence. Again, this reduction is correlated with the reduced pain sensation shown in figure 1 here, red color. However, cartilage-specific deletion of TrkA in these mice didn't do anything. nothing. No improved OA pain or no joint pathology, didn't do nothing. Nothing changed, showing precisely the same as wild type. All right. So the result suggests that loss of nervous spectrum or trigger signaling pathway in cartilage does not affect the progression of OA, hyperalgesia, or pathology. However, I apologize, my phone. However, this result is a little contradictory from other people's paper publications. Sometimes they publish that highly increased nervous spectrum impact on cartilage degeneration, but we didn't see this in our mice study. Now, going back to original orthopedic mystery story, why there's no correlations between the degree of pain and the degree of joint pathology. So our findings show that nervous spectrum enhanced synovial sensory neuron is the key here compared to patient one, is asymptomatic and asymptomatic. This is a key, nervous spectrum and nerve ingrowth is the key, which is very different from diabetic neuropathy. I mentioned that earlier. All right, the nervous spectrum track stimulates VEGF receptor 1 signaling pathway, further stimulating the downstream target pain mediators. Okay, now nervous spectrum VEGF signaling pathways are very closely connected to each other. Now we are talking about VEGF from now. Okay, it's a potent angiogenic factor, and angiogenesis is a striking feature of OA. So we compare the human synovium between normal versus OA, and you can see that in OA, hugely increase the number of vascularization angiogenesis. So this angiogenesis on VEGF induction in OA patients is correlated with the OA severity. All right. One issue working with the VEGF is there are so many VEGF ligands that have redundant and compensatory role. So we thought that targeting receptors would be much better, much more efficient than targeting individual receptor ligands. So in our human tissue analysis, we found receptor 1 and receptor 2, but not receptor 3, are associated with the OA pathogenesis. So we're targeting receptor 1 and 2 now. Also, we want to see what receptors 1 and 2 can do, either OA or pain. Okay, so to understand the role of each receptor, what we did first is we did intraarticular injection of selective ligands for receptor 1 and receptor 2. So this is receptor 1 specific ligands, and this VEGF-E is a very the selective VEGF receptor 2 activating ligands here. Now, when we inject receptor 1 activating ligand into the knee joint in place, they immediately show the pain response. However, we did not see this pain response with the VEGF 2 activating ligand, suggesting that the result suggests the specific role of VEGF receptor 1 maybe in pain pathway. So we did a further investigation. Next, we used conditional Nogan mice for intraarticular injection of VEGF-A. Again, VEGF-A activate both receptor 1 and 2. So now receptor 1 Nogan mice, if you don't have receptor 1, there is no pain. There is exactly same level as a vehicle, PBS level, wild type here. However, VEGF receptor 2 Nogan mice is exactly same wild type, the VEGF injected pain, very severe pain here. Again, our results suggest that VEGF receptor 1 is involved in pain transmission, but not VEGF receptor 2. More genetic evidence here. We use the condition, it's not conditional Nogan mice, it's mutant. So VEGF receptor is inactivated in this mice. It shows that OA after OA induction, there is no pain by this OA induction compared to wild type here, the severe pain here. So further suggesting the involvement of VEGF receptor 1 is specifically in OA pain pathway. Not only in OA, we found inactivation this receptor 1 in mice also abolished disc degeneration induced low back pain without protecting the disc from here. Disc is completely degenerated, just like a wild type. This is a DDD model compared to shape here. So there is no pain, but the disc was severely degenerated in this mice. So our next question is then what receptor 2 is doing here? Nothing. So what we found here, conditional knockout mice of VEGF receptor 1 showed no pain, but no cartilage protection, completely degenerated. However, conditional knockout mice of receptor 2 in mice here showed pain, but protected cartilage. Okay, very healthy cartilage here. Eventually, this cartilage protection reduced the pain because of tissue protection. All right. So these conditional knockout mice models also represent a similar formation. For example, global deletion of receptor 1 or sensory neuronal specific deletion of receptor 1 or astrocyte, spinal astrocyte. As there is a glial cells, astroglial cell, and microglial cell. I don't know, I don't have enough time to explain all those individual, but astrocyte specific deletion in spinal cord in basic, VEGF receptor 1, all of them showed pain resistance. They don't show pain, but without cartilage protection here. So found so far what we found here was the distinct role of VEGF receptor 1 and receptor 2. So VEGF receptor 1 is responsible for pain transmission, and receptor 2 is responsible for cartilage degeneration, as shown here, 1 and 2. Pazopanib is the FDA-approved anti-cancer pain drug, and it can block both 1 and 2 simultaneously. On the other hand, bendatinib is also anti-cancer drug, but specifically and selectively block receptor 2 signaling pathway. So we tested pazopanib and bendatinib in our OA model. Now, 2 times per week intraarticular injection of pazopanib, but not bendatinib. Pazopanib is green color, bendatinib is red color. Only pazopanib shows excellent pain reduction and cartilage protection. I didn't have enough space here, so I couldn't have a pathological analysis here, but I will show you later. We were very excited about our result. However, 2 times per week drug injection frequency is absolutely not acceptable in clinical setting. So to resolve this issue, we collaborated with the PI and UIC, Dr. Liu. She has expertise in nanoparticle drug formulation. So the resulting drug we referred to as nanoparticle 2, which means second generation. We made first generation didn't work very well. So I will show you the data, second generation data. So our collaborator performed optimization, in vitro optimization and characterization of all this encapsulated pazopanib in the PEG. PEG is polyethylene glycol. This is nanoparticles, the size, the distribution, and particle sizes, and also cumulative pazopanib release data show the steadily increased drug release about 70% over 18 weeks. And it shows a multiple independent formulation of nanoparticle 2 showed very excellent reproducibility. So in conclusion, the collective result showed from this the in vitro pharmacokinetics, particle stability, and reproducibility tests all suggest that nanoparticle 2 is good to go to in vivo animal studies. So this is what we have done in vivo study, experimental plan. We did a single intraarticular injection, only one time. Single intraarticular injection in 3 different time points. Group 1 is treatment time point within a week, right after joint injury by PMM surgical procedure, PMM here. Group 2, group 1 is actually inflammatory pain stage. This is not really OA pain. So group 2 is early OA. Now gradually they develop OA by surgery, and then an early OA is about 4 weeks. Pre-treatment time point is advanced OA, or we call it late OA, about 8 weeks post-surgery. So here is the group 1. Let me just share our result for the group 1 first. So group 1 is a treatment time point immediately or within a week, which is inflammatory pain stage. So our weekly pain test result to show that a single intraarticular injection for this drug reduced pain all the way over 16 weeks. It's still very strong anti-pain. So at the moment, we are doing, our question is, how long will it last? So it will last about 20 weeks, 30 weeks, we don't know, we keep going. So far, we are doing actually 18 weeks. So far, good. So I don't know, we still get going. But 16 weeks is long enough for this animal model, so we sacrificed those animals and we did a histopathological analysis. You can see that compared to vehicle, completely cartilage is gone. This drug treatment is showing very healthy cartilage, protected cartilage here. Now this is all 3 groups of the result, group 1, 2, 3. Treatment is right after joint injury. Group 2 is targeting treatment, is the time point is early OA, and group 3 is advanced or late OA pain stage. Now, pronounced pain reduction was observed in group 1 and group 2 specifically. Now, and here are the corresponding histopathological analysis for 3 groups for treatment time point. So our data suggests that nano-PASO 3 effectively prevent cartilage degeneration compared to vehicle and reduces synovial inflammation compared to vehicle here. This is a double immunofluorescence staining targeting pain molecules in the innervating lumbar DIG sensory neurons of both 3 groups, 1 to 3. So our data suggests that nano-PASO 2 suppresses multiple pain mediators shown here in the DIG sensory neurons, including BGF and nervous factor, etc. Now, astroglial cell is the astroglial cell. I mentioned that. Glial cell is very important in pain, chronic maintenance, and disease. So especially astroglial cells are activated in many central nervous system pathogenesis. And we found that spinal astrocytes are also activated in chronic knee-OA pain conditions. Now, no pain, this is intact animal. No activation of astrocyte here. Severe pain in advanced OA condition. Highly activated astrocyte here. Okay, in the spinal cord. This is a spinal cord. A single intraarticular injection of nano-PASO 2 suppressed the spinal glial activity in all 3 groups compared to vehicle group here, including astroglia, the marker is GFAP, or microglia, marker is IBA1. Okay, so these reduced glial activity directly correlate with the reduced pain level. Now, the second student also mentioned about the opioid crisis, but addiction is a big part of opioid crisis and pain management. So opioid receptors are associated with the addiction, as you know. So we want to ensure that targeting BGF receptor, especially 1, or nano-PASO 2 is not associated with the rewarding properties. So drug abuse liability test was done by our company collaborator here, who specialized in drug liability test by comparing morphine here. So result then suggests that, confirmed that targeting BGF receptor 1 or 2 or pasopenic is not associated with the opioid-like rewarding properties. Now, the other one is safety issue. OA is a local disease. It's not systemic disease. So major reason we use intra-articular treatment is that it can minimize any potential side effect compared to systemic administration. For example, pazopanib, what we're using here, pazopanib is originally come from cancer, anti-cancer drug. Cancer patient has to have a systemic administration, okay? So the pazopanib showed, already published well, they showed severe side effect for cancer patient. However, we never have any side effect with the intraarticular injection with the reduced dose, the dose of this pazopanib. So therefore, the safety is not a major concern for intraarticular injection of nanopazo treatment, but we tested the safety using IBIS in vivo imaging analysis. Make sure, just in case. So we used the 3 probes to check. Number 1 is apoptosis necrosis. Number 2, inflammation. And number 3, metabolic changes in the liver. So the white box showing here indicate the liver regions to compare. And we observed absolutely no changes by nanopazo 2 injection and suggesting it's safe so far. In conclusion, a single intraarticular injection of nanopazo 2 has beneficial effect at different stages of OA disease progression by reducing the pain very quickly and catalyst from degeneration. And nanopazo 2 could be promising the drug OA disease, promising OA disease treatment and pain management. We are currently testing the drug efficacy on a larger animal model, like using dogs, and we hope to start the phase 1 clinical study soon. If we can, see the after dog study, larger animal study. And thank you very much for your attention. I'm very happy to answer any questions from our audience.
Thank you very much, Professor Sampen, for that really wonderful and clinically relevant presentation. So any questions? Chinese questions? These are fantastic results. We show that a single intraarticular injection of nanoparts, that it can reduce pain. And you show that for over 16 weeks in the model. So how do you envision this treatment being administered to patients in a clinical setting? And how often would they need to receive the injections?
Yes. Only problem the limitation of our mice model, knee is so small. So maximum we can inject the drug is 10 microliter, that's it. The problem is, it's not problem actually, the nature of pazopanib is very hydrophobic. So when you formulate with a nanoparticle, hydrophobic is good. If it's hydrophilic, that can be a problem. That's why we couldn't do antibody with this nanoparticle, unless you make some kind of linker. But pazopanib is a perfect candidate to nanoparticle formulation for the steady, prolonged drug effect. So, however, because of the insolubility, our maximum drug concentration with the drug formulation is about 13.5 milligram per ml. That is it. So we use the 10 microliter maximum. That's what we show here as a result. However, if you can consider human or dog, the volume it can be mil. It's not microliter level. It's a milliliter level. So for example, 1 or 2 mil if you inject in the knee, then I can imagine it can last 1 year. Because only 10 microliter lasts now 20 weeks. Then 1 mil can easily 1 year. It can be. So that's what I'm hoping. The injection frequency in clinical setting is very important because nobody you can poke your knee every month or every week. No way. Even 6 months, I'm reluctant. If every year I can stand with poking my knee, injecting something that pain for the intraarticular injection in the clinical level. So I'm really hoping in the dog study, we can have a very, prolonged drug effect, for example, about a year, something like that. Then definitely we can see in human condition, we can expect a year of last long, prolonged drug effect. This is my hope. But the going up to clinical level, so many things to, as you know, there's so many things like we have to do the GMP process, the food manufacturing practice, and then IND approval and FDA approval, all sorts of things. So it's a long way to go actually. So, probably at least it'll take about several years to see the result, I guess.
Wonderful. Thank you very much, Im. We have a question from Muskan.
Yes, it was a wonderful presentation, and it's really interesting to know that VEGF and its receptor can be used to as a target for reducing pain.
Yeah.
But I wanted to know about it reduces pain by decreasing NGF and all the pain markers. Okay.
Right.
But what if the patient is already in an advanced stage and the cartilage is already destructed? So the inflammation will be reduced, the nerve ingrowth will be reduced, and all the pain will be decreased with the pazopanib.
That's
Sorry.
okay.
So, but will the destruction be restored? Does it has any effect on the metrics, like increasing anabolic activity or anything, or just inflammation?
You're very smart. Very good question. Thank you very much for asking the question, actually. Yes, that is an issue. So if the advanced stage of the OA, already cartilage worn out, not much cellularity there. So even though blocking VEGF receptor 2 protect cartilage by abolishing those MMP13, ADAMTase 4, ADAMTase 5, uricanase or collagenase or whatever, still there's nothing left already. It's gone. So pain is reduced. Okay, so pain pathway is separate. So pain is reduced, but cartilage, I'm talking about functionality. Sometimes if you don't have cartilage, there is cushioning, no cushioning. It's probably you can make noise, whatever, something like that. It's hard to, stiffness is probably there. So functionality is reduced. So absolutely right about that. So even though pain is reduced, but still cartilage is, we need to regenerate, okay? So next our chapter is we involved together with the stem cell injection, cell-based injection, together with the pazopanib co-administration. That is our next step. Actually, we have some preliminary data, but I didn't want to mix up, so I didn't put it here. So thank you very much. That's a very brilliant question.
Thank you. Thank you for answering. I really enjoyed it. Everything was really covered. I had a question and it was answered directly in the next slide. So this was the last question that came to my mind.
Oh, that's wonderful. I wish I can have more detail, like if we pain tested, how we doing, something like that, showing picture, movie showing what we do, something like that. But otherwise, it takes probably several hours. So that's why, probably watching. Yeah.
Yeah, I really enjoyed it. Thank you.
Thank you very much.
Any other questions?
I do have one actually, if you don't mind. I am, fantastic work as usual. Very wonderful talk and lots of very impressive data, very promising.
Thank you.
I had some questions about the patient. I was curious actually. So you mentioned 40% of patients that I actually didn't know that who are grade 4 OA actually don't have major symptoms despite their cartilage being damaged or I would imagine osteophyte growth and so on. Right. And then in your animal models, which are quite impressive as well, you targeted the VEGF receptor. R1 and 2, of course, and R1 responsible for pain. In the patients, for instance, you did show data about the vascularity. So there's the synovial membrane. The ones who are symptomatic, you showed an increase in vascularity and thickening, I would imagine, of the synovial membrane. So if we're going back to the patients now, going to the translational part, in these patients, are there differences in the expression of the VEGF receptor 1 and 2, or what would distinguish them for their pain sensitivity? And did you happen to try heterozygote animals to see if you just maybe knock down half of the receptors, let's say half of R1, if that would have some sort of effect as well on pain, like a half response or something, and whether that could try to delineate a little bit more about what's going on in the patient setting, why some are maybe sensitive or less sensitive?
Yes, good question, actually, great question. That's why in the OA risk factor, in there, I say the genetic variant, genetic background. So, some people have, for example, let's assume the gene copy number of 10. Some people have 100, something like that. So if you have another risk factor, reduce the copy number, probably expression is very low. I think everybody has those genetic backgrounds, makeup is different. So that gives you this pain perception, and everybody said all brain, it is all your brain. But actually, I think it depends on how many receptors you have, how many more copies of it. I think it all depends. So you cannot really judge it by, I don't feel pain. How can you feel pain? Don't be chicken. I cannot say that. It all depends on receptor number, I think. So I absolutely agree with you. I think depends on what gene expression is, how made of. I think that gives you more pain sensitivity. Really. There are, even myself, I'm very sensitive to pain. That's why probably I enjoy my pain research. I'm very afraid of pain. Of course, that is another factor. Pain perception is stronger because psychology effect is also another one. Depression is another one. So all those factors are actually giving me more pain and less pain or something like that. But, the OA pain, again, I think you heard about it, radiographic knee joint, that, the radiographic result, it doesn't really match with the pain degree. It's already well published. So why? I think try to understand, yes, this is one reason. Genetically, if you have less growth factor, copy number, then probably you are a little insensitive compared to other people. This is only what I can say at the moment. So, about 10 years work, and the contribution is so small, maybe this one, but this is only what I can do, honestly. I don't have any definite answer, but I'm trying to understand how maybe that's the one reason, that's all.
Yeah, I imagine that's difficult to compare between patients, of course. You have the psychological aspect as well to compare, it's not very direct.
Yeah. But still, we don't have a very clear answer why. But at least we see that the huge difference in nerve growth. And nerve growth factor is nerve growth factor and VEGF, both.
My other question is actually the nanoparticles are quite impressive. So is there a pH effect on release? Because I know you showed in the slide showing I guess that was published, the effect of pH 3 and 5 or so on the release profiles. So in the synovial fluid, you're looking at 7 or 7.5 or so on, I guess, depending on how inflamed the tissue is. Wow. Are there effects there?
Mike, you're very sharp. How did you see that? Yes, it is. It is. So the next our step is we are using synovial fluid to see that the particle release from the particle, how the drug release patterns. Is it the same, the totally different pH and something like that? We are looking at. Very, very sharp. Yes, so that's our next step.
Perfect. Yeah. One more question, actually. Sorry to belabor it.
That's okay.
But I was curious about the pazopanib. So targeting the VEGF, knowing that the synovial membrane is highly vascularized. So do you predict any like a long-term effect, or so for treatment, do you predict to use like a short-term use, like a relatively short-term use for targeted pain, or is it going to be something a treatment that you're going to take for prolonged periods of time and with potential side effects on the synovial membrane?
Synovial membrane, you mean by intraarticular injection?
Yes, yeah.
I think it's, the number one, only if you're just using pazopanib itself, then it will clear very quickly. So that's why we use it twice per week injection in order to maintain pain level reduction. However, this pazopanib 2 is nanoparticle conjugated, encapsulated, so it's long term. That's what I said, maybe yearly, once a year injection that keep going on pain reduction. That means that particles slowly degenerated, the particles, and then slow drug releasing effect there. That means it's a chronic impact there and a long term, 1 year by single intraarticular injection. So I think my understanding is a synovium. I think there is no big trouble inhibiting those VEGF level, because if you knee joint pain, we don't want the nerve ingrowth into the knee joint. That's how we have when you have OA. It's always nerve growth inside. So in VEGF, it blocks those things. The other one is, indeed, the VEGF receptor 1 is not really angiogenic, strong angiogenic. Receptor 2 is. Receptor 1 is so, but the reason is, that's the reason every drug, anti-cancer, whatever, they developed the drug based on VEGF receptor 2. This anti-angiogenesis, anti-cancer, all of them. Receptor 1 and drug development just recently, we found out receptor 1 is anti-pain. It's a totally different mechanism from angiogenic factor. So we call that it's merely beyond angiogenic factor. That's what we call it. So receptor 1 of angiogenic event is nothing to do with, it's not really overlapped with the angiogenic factor. That's what I would say. So beyond the angiogenic, the function of VEGF receptor 1. That's what I would say. Is it answer to your question? I'm not sure.
Yes, yeah, perfect. Actually,
Okay.
thank you.
Okay.
That's really wonderful. Absolutely sublime. Thank you very much.
I wanted to see you all, actually. Thank you, Jackson, having me here. I really enjoyed seeing you guys. Thank you.
Yeah, thank you everyone for attending. I think next week will be our last meeting. It's the one about patents that was answered. So it will be our last meeting. So you can take a break for spring, enjoy the nice weather. So
Yeah.
bye everyone. And thank you, Michelle, Kadir, Muskan. Thank you, everyone.
Thank you very much. It's a student, they are really wonderful. Thank you.
Yeah.
Thank you. Thank you so much.
Thank
Yeah, thank you.